Now, in this section, we're going to talk about the concept of heat. And what we can generally say is true for thermodynamic systems or systems where we want to describe the transfer of heat from one object to another. It could be from the heated gas molecules of a flame on the stove to the silver pot that is being heated. We, in this case, talk about the transfer of the internal energy from one object to another due to a temperature difference. One example I like to bring up is suppose we have a hot iron brick uh, sitting right next to or in contact with a cold iron brick. There will obviously, from our experience, we know there will be an increase in the temperature of the cold brick and a decrease in the temperature of the iron brick until the two reach equilibrium. And generally speaking, we could say that if the hot iron brick, has the same mass as the cold iron brick, then they will, in the absence of any other thermal contact, the uh, the the hot iron brick will transfer its internal uh, energy, which is it's the kinetic energy of motion of its molecules, from the hot iron brick to the cold iron brick. Therefore, the internal energy or the vibrational motion of the iron molecules in the cold brick will become more vigorous. That is to say, the vibrations will increase, and this increase in vibrations of the atoms of the iron brick will cause its internal energy to increase. And that flow of internal energy from the hot brick to the cold brick is what we call heat. Um, and their temperature will equalize when the temperature of the hot brick reaches the temperature of the cold brick. And as I said just a few moments earlier, if they were equal masses in the two bricks, then they would reach their equilibrium temperature halfway in between the initial cold temperature of the cold brick and the initial hot temperature of the hot brick. So, flow of internal energy, it goes from a high temperature substance to a low temperature substance until this equilibrium is reached, and the internal energy never flows unassisted from a low temperature to a high temperature. It always flows from the high temperature to low temperature, which is sort of what we might expect intuitively. And based on the previous discussion, I think you'll be able to answer this by yourself. I'll just put a pause in here, and you can answer this, and then see the answer on the next slide. So, as we've been saying in the last few slides, the heat is a measure or is a quantity of energy transferred from one object to another. We normally designate this by the letter Q when we use it in equational form, which we will discuss later. It is measured in units of joules or calories. If we apply, for example, 4,180 joules of mechanical energy by shaking or stirring 1 kilogram of water, that will raise its temperature by 1 degree. This was a measurement made early on by scientists. I believe it was the scientist named Joules who did the original experiment, and basically found that there is an equivalence between, or what we can increase the internal energy by shaking or stirring a mass of water until its temperature increases, and thereby we apply mechanical energy. That is a becomes known as or is equivalent to to the same amount of heat being applied to raise the temperature by 1 degree. Because we use a different unit for describing the a unit of heat as known as a calorie, we'll give its definition here. Basically, what a calorie is it's the energy required to raise 1 gram of water by 1 degree centigrade. So, based on what we said earlier, if I divide the 4,180 joules by 1,000, and I divide the 1 kilogram mass of water by 1,000, then I have 1 gram, then it will require 4.18 joules to applied to 1 gram of water to raise it by 1 degree. From this, we can see that the equivalence between joules and calories can be made by stating that 1 calorie is 4.18 joules. Now, the reason we talk about calories as a unit of heat is in the food industry is that the energy ratings of foods are determined from the energy released in the form of heat when they are burned. So our body, after consumption of food, produces chemical reactions in the body that causes the heating up of the blood and the tissues of the body. One can understand this quite simply from the point of view that while the outside temperature is 70 degrees, our internal body temperature is 98.6 degrees Fahrenheit. And that can only be maintained or achieved if we are consuming foods that will cause the body to heat up. And we have to stay at that temperature to remain healthy. Therefore, we have to be at a higher temperature than the atmosphere outside, and therefore we have to continue to consume food every day in order that our body temperature does not equilibrate to the surrounding temperature of our environment, which would be normally 70 degrees Fahrenheit, which is 28 degrees colder than what our body is maintaining. So we are continuously radiating heat as a result of the consumption of the food molecules, and that heat is causing that heat that's being released from our body to the air around us will cause a drop in the temperature of the body unless we maintain those chemical reactions to keep producing more heat. So the body is does a very efficient work at regulating its temperature to 98.6 degrees, which is 28 degrees warmer than the surrounding temperature. But it must continue to burn those calories or to generate or to heat up the body in order that we stay at a temperature that's above our surroundings. One other point that's worth noting here is that in the common food industry, the way they define a calorie is really what we call 1,000 calories. Therefore, when you see a box saying this quantity of food has 460 calories, they, in the physics sense of the word, they are saying that there is 460,000 calories. So their calorie is really what we call in physics, a kilocalorie. And the same is true as before. The heat needed to change the temperature of 1 kilogram of water by 1 degree will be, in fact, 1,000 physics calories, which is which is called 1 calorie in the food industry. Now, in this slide, we are asked to consider adding a fixed quantity of heat to two different volumes of water. and they are in two equal sized containers, which is irrelevant for the point of the discussion. So we can this. I'm going to let you know that in advance. But let's say what it's basically telling us is that I have a fixed amount of heat that's added to a kilogram of water, and then on the other hand, another experiment, I have the the same amount of heat added to 2 kilograms of water. What will be the temperature increase of the smaller amount of, of water? Will it decrease? Will it increase? Will it not change? And I'll let you make your answer decision, and then you can see the slide answer when you go to the next slide. In this slide, you are asked to consider um, the two scenarios, one in which a fixed amount of heat is added to half a cup of tea and it causes the temperature to rise by 4 degrees. And then the second scenario is that same amount of heat is applied to a different cup, which is the same size cup, but it is full of tea. And now the question is, how much change will occur in the temperature for those uh, for the full cup of tea? So I'll let you think about this and answer it, and then we'll resume after the answer. In this part of the lecture, we're going to introduce a new concept called the specific heat capacity of a mass. The mass could be a mass of air. The amount of we could be the sum of or all the air molecules in the room. We could be talking about the heat capacity of a cauldron of iron over a stove or fire. We could be talking about the heat capacity of a coffee cup or any object. It could be solid, liquid, or gas phase. But the general property that one is aiming at defining here is the concept that's most similar to the inertia experienced by the force on an object that we talked about in the earlier sections. And if you see the fourth bullet point, it says it is like thermal inertia. It's the resistance of a substance to a change in temperature. And basically, what this means is that I can have two different types of material. We'll give the example of a silver pot and an iron pot in a minute. But I apply the same amount of heat to the silver as I do to the iron. Will the increase in temperature be the same? Well, generally, no, it's not. It depends on which materials are involved. But the way we define the heat capacity is that if the temperature rise is less for the same amount of energy that I'm putting in, then it has a lower heat capacity than an object where I apply the same heat, but the temperature rises substantially higher. So this is similar to the idea of trying to accelerate a heavy object and a large object. If I apply the same force to the large mass as I do to the small mass will accelerate more. And in this scenario, what we're doing is we're applying the same amount of heat to the um, uh, to the um, to the silver pot as we do to the iron pot, and observe which has in this case the same grams of material, so its weight is the same whether it's silver or whether it's iron, but by applying the same amount of heat, even though their masses are the same, the the silver pot will go to a higher temperature than the iron pot. And therefore, the iron has a more thermal inertia. It produces a smaller energy change for the same amount of heat that's being added to it. Now, the way we quantify this numerically is in the quantities is joule per gram of matter uh, per degree Celsius. And so what this means is, if I take the case of water, for example, that if the specific heat is 4.18 joules per gram per degree, then what it says is that I have to add 4.18 joules of energy to raise the temperature of 1 gram of water by 1 degree Celsius. And it turns out that has one of the highest heat capacities of all the substances in the world, which means that it requires the most energy to heat up to a given temperature. And that is why also, by the way, a side note is that once it's heated up to a temperature of, say, the boiling point of water, it takes the longest time to cool down compared to other materials. And that turns out to be very important when we're considering the thermal effects of seawater moving across the oceans to different coastlines on the continents. We'll discuss more about that when we discuss the meteorology or the weather systems in terms of their flow. Now, this slide gives us a similar example as the one we talked about in the last slide, namely what it's indicating to us that different materials have different heat capacities or different thermal capacities for storing energy, or to say it another way, they require different amount of energy to raise its temperature by 1 degree, assuming that we have the same mass for each of the objects under consideration. Now, example of this would be, let us suppose that I have a pot of water which I want to raise to the boiling. I want to raise to the boiling point. We find that if we do the experiment using an iron pot, it takes about 2 minutes to raise the temperature of an iron pot of water to the boiling temperature. Whereas if we apply the same amount of heat or heat rate, if we apply it that same, not the same amount of heat, but if we use a silver pot, then it takes only half as much heat to raise the temperature of the same quantity of water to the boiling temperature. So this indicates then that the silver pot, having the same mass as the iron pot, will heat up more. Will heat up more quickly. It will reach a higher temperature more quickly than the other. Therefore, the iron has a higher specific heat capacity. It has more resistance to the change in temperature. Since we need to boil the water to get the food cooked, then we can see that taking twice as long to get to the boiling temperature of water means that it is going to take twice as much heat to get that iron pot up to the boiling temperature of 212 degrees. So this is what we see as a practical example of the difference in the heat capacity of silver versus iron. In this example, we compare the specific heat capacity of water to that of iron. And the observation here is that if we add 1 calorie of heat or energy to 1 gram of water, it will raise the temperature of that gram of water by 1 degree Celsius. At the same time, we observe that it only requires 1/8 as much energy to increase the temperature of 1 gram of iron by 1 degree Celsius. So in this case, it would be 1/8 of a calorie to raise the temperature of the iron by 1 degree. So therefore, water absorbs more heat than iron for the same temperature change, and we therefore say that water has a higher specific heat capacity. In numerical units, we've stated before that the specific heat capacity of water is 4.18 joules per gram per degree. So taking 1/8 of that, we can say the specific heat of iron would be roughly approximately 4 divided by 8, or 1/2 joule per gram of iron per degree Celsius. So that gives us the 1/8 heat capacity that this is indicated here in the slide. Now, because water has such a high specific heat, it can store thermal energy much longer than other substances before cooling down to, say, room temperature. So there were times in the distant past, before we had modern heating facilities, that people would use hot water bottles to keep their beds warm in the evening, because the water stored the thermal energy much better than other liquid substances did, and therefore were very, very slow to cool down. And we'll see this in the next slide, that water cooling, because it takes so much heat to raise its temperature, it retains its heat better, and it takes a longer time to cool down. So a higher specific heat means longer cool down time, or a better ability to store its thermal energy. Now, the reason why this turns out to be the case is that when you apply heat to a substance, that heat is absorbed or as internal energy into the substance, whether it's water or iron or some other liquid. So that internal energy can go into multiple different pathways. Only one of those pathways ends up increasing its temperature, and that is the translational kinetic energy of the molecules of the water, um, which will cause which causes the increase in temperature. The other mechanisms that do not increase temperature are the internal vibration or rotational motion within the molecules, and this does not affect the rise in temperature. It also, the increase in the jiggling motion of the however the I should say the increase of the jiggling motion of molecules, which is the translational kinetic energy, does in fact raise the temperature. So if it goes into the pathway of increasing its internal vibration or rotational motion, uh, then that does not raise the temperature, and therefore, let's say, for example, only 1/4 of the heat transfer goes into increasing translational kinetic energy, then its temperature is not going to rise as much, because the other 3/4 of the energy is going into other forms of internal energy which are not related to the temperature increase. Now, another example of the high specific heat capacity of water can be seen in the water currents, the effect that water currents have on the air temperature as they flow in the North Atlantic Ocean. Um, Generally, one can see from the circles on the map that water passes into the Caribbean in its closest approach to the equator, um, as it circulates clockwise through the Atlantic Ocean. In that region, it acquires the greatest amount of heat from the sun, and therefore the internal energy of the water is increased by its contact with its sun. And because of this increase in internal energy, it will gradually cool as it goes northward, first up the North Atlantic coast, and then over into the European coast. But the release of that heat happens in such a slow time frame that the water temperature over the European coast is still quite a bit higher than the ambient temperature of the land. And as a result, the slow release of the thermal energy of the ocean causes the air above it to gradually get heated up, but some of that heat does not get released until the water reaches the North Atlantic, the European coastline. Therefore, any heat that is released is goes into the westerly winds that blow across the European coast and keep it warmer than it would otherwise be enabled to be. Effectively, the heat absorbed in the Caribbean is used to warm the European coastline because of the very slow release of internal energy to the atmospheric winds above the surface of the ocean. Now, before answering this question, I want you to think a little carefully of what the picture in the on this slide is indicating. What happening here is that the way to think about this is that we have an equal amount of sunlight hitting. Um, we will say a square meter of ocean water as the square meter of land. And so the red rays that you see are heating up the water and they are heating up the land. The energy that is being pumped in um, from the sun is a form of heating, and that heat represents an increase in the internal energy of the land mass or the water mass, depending on where the rays are falling. What you see here is that the temperature of the land surface or the Earth's surface has risen to a higher temperature than the surface of the water. And the reason this happens is because the specific heat of the water is nearly higher than almost all of their substances, and therefore it will have the highest thermal inertia. So I've already answered the question, but I think it was important to try to explain it anyway, and it shows you the fact that you can see in this picture that both land and water have received the same amount of radiant energy from the sun, but the temperature of the land has increased more than the temperature of the water, tells us that the specific heat of water is still much higher than for land.